All right, gang, Math 5500, more on checking assumptions. The goal of this is going to be a very brief video, unless I get on some tangents, like, happens from time to time. But I'll fight the urge, all right? So the, the purpose of this video is just to dive into simple linear regression assumptions even more. And again, compared to other techniques where you check assumptions before you run your model, like ANOVA will check equivariance and normality. I mean, you'll learn that in 6610. It's reversed with regression. We have to create our model first, and then use the errors that we create from the model to test the assumptions. So it's kind of strange. But the purpose of this video, you can see I have a data set loaded in R called admit rank, and there's three variables. What we'll do is we will predict the GPA from GRE, and then maybe even the rank. Rank is I don't know what's going on with rank. Looks like they have the percentile ranking, so it looks like they have the bottom 25%, the middle, or the 25 to 50, and 50 to 75, and then so it looks like it's some sort of percentile ranking that they give. So it would make sense, me as director of the program, to see, is there a relationship? Can we predict first year GPA from GRE and rank? All right, now the main thing I want you to see is that the data sets that I created in the previous video, I created those. Those were custom made to make a point. The first one looked like it was linear. Once we tested the assumptions, we saw that we didn't have equal variance, we didn't have normality, so we violated some stuff. The second one even failed the eyeball test. This stuff's much more effective, I think, and once we get a larger data set. So that's the purpose of this. All right, so assumptions. Let's talk about assumptions. The simple linear regression assumptions are that our errors are independent. This is something that's usually checked, I would say qualitatively, if you will, in the design of the study. We want linearity, in other words, that our y's are a function of our x's via a linear function. We want constant variance, we call that homoscedasticity. An extra credit question on your final exam may be spell homoscedasticity. Maybe just say pronounce it. And the final assumption is that our errors follow a normal distribution. Now we've seen that we can check this with the QQ plot. We can check the linearity with the residual plot, and constant variance with the linear residual plot as well. So let's do it. The first thing I would want to do, if I'm predicting GRE or GPA from GRE. All right, so the first thing I'd want to look at is just kind of get to know my data. Remember, correlation of XY is the same thing as YX, so it doesn't matter. So we have a moderate correlation between GRE and GPA. Now, let's stick with the path, okay? That tells us a little bit, but not a lot. All right, so let's look at GRE over GPA. And you know what? Just as I would predict, I don't see a linear pattern at all. When I visualize my line, I see a whole lot of assumptions that are very, very likely to be violated. Next thing I want to do is I want to create my model. So I'm going to predict GPA from GRE. And what I want to do first of all is I want to look at my predictor, right? Well, my predictor, GRE, is statistically significant at the .001 level. The test statistic is 8.3, extremely small standard error. And we would use, since we're looking at a one predictor, we would talk about R squared using the multiple R squared. So we could say that 14.8% of the variance in GPA is explained by the regression on GRE. So you need to tattoo that one to the brain, because that is something that I will definitely ask when it comes to high stakes. Next thing I'd excuse me. Next thing I'd want to do is look at the model. It's redundant in this case because we have one predictor. And we're going to transition all this into the multiple linear regression case in the next video. But, we get, again, our model is statistically significant at the .001 level, which is always the case when we have one predictor. If our sole predictor is statistically significant at the .001 level, then our model will be statistically significant at the .001 level. Because if we got one predictor, our model is, that's all we got is one predictor. Our model is that predictor. Not so with multiple predictors in multiple regression. So next thing I'd want to do is just kind of jump right in. R has this really cool little feature where it gives you 4 plots from once you create your model. So I would look at this, and I tell you, my model with the residuals and the fitted value isn't as bad as I would have thought. In fact, it looks like the linearity assumption is met. We have no pattern per se. There are some red flags, and we have a flat red line. So we check a lot of boxes with this. I'm a little concerned that the variance in the higher GPAs, about the same as the middle GPAs, but in the lower GPAs, I don't see as much variation. But again, would I feel comfortable checking the box that the linearity assumption and equal variance is met? Yeah, you know what? I probably would. Let's check the QQ plot. With this, we're checking the normality assumption. Yeah, we have a little bit of deviation. I have no issue whatsoever here, but for the ordered theoretical quantiles up around the 2 and the 3, you can see that we do have some deviation right here. I don't think that's enough to warrant a transformation, which we'll talk about in 6500. Yeah. I would probably check the box, noting my concern with this, and move forward. The next 2, again, are checking nonlinearity and non-constant variance, as well as other issues. Again, no real red flags there, and no real red flags there. So this model was actually turned out to be more impressive in terms of checking the boxes for the assumptions than I thought it would be. So, what happens here is we know that we can create our predicted by just looking at the fitted of the model. And of course, we can always get our errors, our residuals, by taking the observed y, which in this case is the GPA, minus the predicted. And another way of looking at equal variance is to plot the errors over our x variable. So that's what I could do here. I could plot our x, which again is GRE, over our errors. And you're going to see a plot that looks very, very similar. In fact, almost the same thing. In fact, it is the same thing. I'm being goofy. As we would get if we put our fitted values here, right? Yeah, so why don't we do that? Well, we can in the simple linear regression case because we only have one predictor. But when we, let's just revisit this, a more effective way moving into and you'll see it's the same, it just doesn't have the red line. You'll see that this was nearly identical. With the residuals plotted on the vertical, but our fitted values here. Again, moving into multiple regression, we don't have a single x variable predictor, so we need something that works more universally. Well, as promised, this was a short video, so again, the scatter plot that I eyeballed early on, started out with it's kind of a low correlation. We looked at a scatter plot, so we eyeballed the relationship. I wasn't impressed, but as I dug in a little deeper, the assumptions for using a linear model appear to have been met, at least with the tools that we currently have. So, again, I could, to get a better look at that, let's just plot GRE with GPA, and then let's do abline for the model. So we get this relationship between x and y, which is, yeah, I'm still not that impressed, but again, theoretically, I think if you were publishing this, you would have the you would be able to check the assumptions for moving forward. All right, gang, that's all I got.